The next thing on Wesley Clark's sketch is looking at angle sums, and I think you're probably already pretty familiar with this, and we discovered this in our work before. But here is a triangle here, and it is the angles are controlled by these sliders, and notice that we do get infinitely many triangles with the same size. Okay. Which, by the way, right there tells you that the angle situation is not going to be enough to lock down the triangle. But if you see the third measurement here, notice that it always stays the same. We can adjust this, and we get the same measure. Some of these are negative because they're directional, depending on how we orient this. Okay. So that's an important thing about Euclidean triangles, is that the sum is always the same, and so we can see that sum, and that sum is pi radians, or 180 degrees, and it really doesn't matter what the angles are. It always turns out to be the same sum. Now it turns out that this is closely related to the Euclidean parallel postulate, that through any point not on a line there exists exactly one line through that point parallel to the given line. Turns out that that's equivalent to this. So if you assume the sum is pi radians for the angles, then you can prove the parallel postulate. Or if you, like we do, can take that as a postulate for Euclidean geometry, then we will be able to prove this here as a theorem. We'll do that a little bit later on. But actually, it's even more remarkable than that. You can actually prove that if this sum is any constant, that constant has to be pi, and that that the parallel postulate holds. So contrast that with the hyperbolic sum here, hyperbolic angles here. So here we can specify a couple of angles, and we can show the third angle and the angle sum. But what's interesting is notice as you move this around in different places, that third angle changes size, and the sum is different. Also notice that the sum is always less than pi. Look at these numbers, they're less than pi. And so as we get this closer and closer to smaller and smaller, it gets really close to pi. As this triangle gets disappeared there for a second, as it gets really big, then like that one, for example, now we get further away from pi. You know, it's actually less than half a pi there for the sum. So it's interesting to see that there's something there that has to do with this geometry that's a little different. So the angle sum is not constant, it's variable, and the angle sum is always less than pi. And of course we also looked earlier at the spherical geometry in earlier videos, both in using the sketch that we were looking at from Brad Findle, and then also with our linear spheres. We found that in spherical geometry the angle sum is always larger than pi.